In this lesson, we'll look at polynomial functions. In particular, we'll look at the end behavior of polynomial functions. We'll identify zeros and the multiplicities of these zeros, and we'll learn to sketch graphs of polynomial functions. We start with the definition of polynomial function. Let n be a positive integer, or 0, and a naught, a sub 1, a sub 2, all the way up to a sub n be real numbers with a sub n not equal to 0. Then f of x equals a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power plus all the way down to a sub 1 times x plus a naught is called a polynomial function of degree n. So the degree is the highest exponent in this polynomial. These a's that are indexed are called coefficients. And the index is the number that is a subscript. Those correspond to the power of x that they are attached to. So for example, we have a sub 1 times x, which is really x to the first. And here in the middle we have a sub n minus 1 times x to the n minus 1. Of course, this is just the general way of writing and expressing a polynomial. N will have some positive integer or 0 value, and then you'll just have that many terms for your polynomial. Example 1. Determine if the following are polynomial functions or not. A, f of x is equal to 3x plus 2. First off, do you have x's that are raised only to integer, positive integer powers? The answer is yes. And then are your coefficients real? Yes. So yes, this is a polynomial. B, f of x is equal to 8x to the 12th power minus 3x to the 11th power plus 2. Again, are your x's raised to positive integer powers? Yes. And do you have real coefficients? Yes. So you have a polynomial. Question C. F of x is equal to the square root of x. In this case, the square root of x can be rewritten as x to the 1/2 power. You're not allowed to have fractional exponents in order to be a polynomial. So this one is no, not a polynomial. D, f of x is equal to 4x plus 1 over 8x minus 3. This one is no, not a polynomial, because you're not allowed to have x's in the denominator. And then part E, f of x is equal to 2ix squared. There's no problem with the x's. This time it's the coefficients. This one is going to be no, because the coefficient must be real. And of course we know that 2i is complex. So that is not a polynomial. Polynomials have names based on their degrees. Recall that the degree is the highest power in the polynomial. If you have a polynomial of degree 0, we call that a constant. And an example of a polynomial that is a constant is f of x is equal to -3. It's just the number. A polynomial of first degree is called linear. And we've studied these before. An example would be f of x is equal to 2x plus 5. So the degree is 1. That is the highest power of the x. That is x to the first. A polynomial of degree 2 is called a quadratic. We've studied these before as well. For example, f of x is equal to x squared minus 3x plus 4. A polynomial of degree 3 is called a cubic. And for example, we have f of x is equal to negative 7x cubed plus 3. Notice we don't have all of the terms, the x squared or the x to the first. That just means that the coefficients for those terms are equal to 0. A polynomial of degree 4 is called a quartic. You can remember this several ways. How many quarts are in a gallon of milk? There are 4 quarts. Or how many quarters are in a dollar or a football game? There are 4 quarters. And this is the root quart, which means 4. So for example, f of x is equal to x to the 4th plus 5x cubed minus 7x squared. And lastly, a polynomial of degree 5 is called quintic. And you can remember this one based on the word quintuplets. That's what it's called when you have 5 babies at the same time. And an example would be f of x is equal to 3/4 to the 5th power plus x to the 4th minus 2. One important aspect of polynomials is their end behavior. The end behavior of any function is the direction of the function values go as x goes to negative infinity on the left side of the graph and as x goes to positive infinity on the right side of the graph. For polynomials, the end behavior on both the left and the right sides of the graph can be either positive infinity or negative infinity, and other types of functions will have different behaviors that we will study later in this course. So end behavior is just looking at what happens on the left end of the graph and the right end of the graph. It does not concern itself with what happens in the middle of the graph. The end behavior for polynomials is based on 2 aspects. The first one is the lead coefficient, or the leading coefficient, a sub n, and the degree itself, n. So once you know these 2 things, then you can figure out the end behavior for any polynomial. Here's a chart to help you remember the end behavior. I'm only going to draw the left and the right ends of the graph. We're going to leave the middle blank because the middle changes based on other aspects, and they do not concern themselves with the end behavior of the graph. Starting in the first box, if you have a leading coefficient that is positive and a degree that is odd, then the end behavior on the left goes down, and the end behavior on the right goes up. And then, based on the polynomial itself, the middle will do other things. If the leading coefficient is positive and the degree is even, then on the left side, the end behavior is up, and on the right side, the end behavior is up. If the leading coefficient is negative and the degree is odd, then on the left side, the end behavior is up, and on the right side, the end behavior is down. And finally, if the leading coefficient is negative and the degree is even, then it's down on the left and it is down on the right. Now, one way to remember these is to think about the typical functions that these would be. What is the basic function that has a leading coefficient that is positive and an odd degree? That would be x cubed. And you know what x cubed looks like. It starts down low on the left and then goes up to the right on the right side. What function has a leading coefficient that is positive and is even degreed? That's x squared, and you know that that is your basic parabola. It goes up on both sides. Notice how these two graphs match the two graphs on the left side in the chart, the in behavior. The function that has a leading coefficient that's negative with an odd degree is negative x cubed. That's the reflection of x cubed. So it's up on the left and down on the right. And finally, negative leading coefficient with an even degree is negative x squared. It's down on the left and the right because of the reflection of the parabola. So these typical functions will help you remember the in behavior of polynomials. Again, it's based only on the leading coefficient and the degree itself. Let's look at example 2. Find the in behavior of f of x equals negative 7x to the fourth plus 5x cubed minus 2x squared plus x minus 3. So the first thing we need to identify is the leading coefficient. That's negative 7. Remember, the leading coefficient is the coefficient of the term that gives us the degree. And we don't care that it's negative 7 as much as we care that it's negative. And then what is the degree of this polynomial? The degree is 4. And we don't care so much that it's 4, but we do care that it is even. So refer back to your chart. What is the in behavior of a polynomial whose leading coefficient is negative and degree is even? It's down on the left and down on the right. So we would say that the in behavior here is down left and down right. Another way that some people write in behavior is the following. You would write this statement. As x goes to negative infinity, f of x goes to blank, and as x goes to positive infinity, f of x goes to blank. And you would always write this statement for in behavior. The in behavior then just fills in the two blanks. As x goes to negative infinity, that's talking about the left in behavior. And what does the graph do on the left end? It goes to negative infinity because it goes down forever. And then as x goes to positive infinity, this is talking about the right end of the graph. What does the function values do? They go to negative infinity as well because it goes down on the right. Remember that f of x really means the y values. So you're tracing out where the y values are going as the x is going to the left side and toward negative infinity, and as x goes to the right side and toward positive infinity. Example 3. Find the in behavior of f of x equals 3/2 of x to the fourth plus 1/2 x to the fifth. We need to identify the leading coefficient and the degree. Now notice that this polynomial is not written in descending order where the exponents are lined up correctly. That means that the term that gives us the leading coefficient and the degree are not the first terms from the polynomial. They're still the leading coefficient in the degree because they come from the x with the highest power. So the leading coefficient is 1/2, and that's positive. And the degree is 5. More importantly, it is odd. So let me draw the typical in behavior of a polynomial with positive lead coefficient and odd degree. That's down on the left and up on the right. So we could say down, left, and up, right. Using the alternative statement, as x goes to negative infinity, f of x goes to blank, and as x goes to positive infinity, f of x goes to blank. And we would fill these in with the appropriate infinities. Since it's going down as x goes to the left, we would say that as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, since the function is going up on the right side, we would say f of x goes to positive infinity. Another property of polynomials is that they are smooth and continuous. Smooth means that there are no sharp corners or points. Continuous, informally, means that it can be drawn without lifting your pen. Let's look at example 4. Determine if each of the following graphs can be represented by polynomials. The first graph should look familiar. Notice that right here at 0, we have a very sharp corner. The graph comes in from the left and abruptly turns and moves up in a different direction going to the right. So this is not a polynomial. And it's because it has a sharp corner. At x equals 0. Since it has a sharp corner, we say that it is not smooth. The second example, the graph comes in, and if I were to draw this, I'll draw it here, and then all of a sudden I have to jump down from this point down to around this point and then continue off. Since I had to jump from one point to the next point, this one is not a polynomial. Because we have a jump at x equals 2, and therefore it is not continuous. So not continuous implies not a polynomial. In the third graph, notice that I can draw it without lifting the pencil, so it is continuous. And secondly, there are no sharp corners. Everything is very smooth around the edges. When it has to change direction, it does so very smoothly. So this one is smooth and continuous. and therefore it is polynomial. One other property of polynomials is the number of turning points that they have. So the turning points are just where the graph changes directions. We are already familiar with this with the parabola. You know that if you start graphing a parabola, it has one turning point right here at this top point here. These turning points reference back to the relative min and the max. So this one comes from x squared, and the statement is a polynomial of degree n can have at most n minus 1 turning points. So the degree of a quadratic is 2, so it can have at most 1 turning point. That's why parabolas don't reach their maximum and then start going down and then suddenly turn around again. It's because they can only have 1 turning point. If you look at a cubic, x cubed, it can start low and have a maximum and then come back around, and then it can have a minimum and it can turn around again. A cubic can have 2 turning points. Now you can also have a cubic that doesn't have any turning points. So the statement is that it has at most n minus 1 turning points. It doesn't say that it has to have n minus 1 turning points. It's just that it can have only at most n minus 1. Example 5. How many turning points at most can the polynomial function g of x equal 15x to the 7th minus 3x to the 5th plus 2x minus 9 have? So simply, you find the degree is 7. So the number of turning points at most is 6. It has 1 less than the degree. Finally, let's look at the zeros of a polynomial function. Recall, the zeros of a function are the values of x where f of x is equal to 0. These are also called the roots of a function. Further, if the 0 is real, not imaginary or complex, then it corresponds to an x-intercept on the graph of f. If the function is in factored form, and the factor x minus c is raised to the m power, so this would be x minus c raised to the m power, in the factorization, then we say that c is a 0 of f with multiplicity m. So the multiplicity of a 0 is the number of times the factor would have occurred had you written it out the same factor over and over and over. X minus c to the m means that you would write x minus c times x minus c times x minus c dot 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 a total of m times. And for every time you would write x minus c, that produces the same 0, but then you have a total of this number occurring m times. The number of times that that 0 occurs is called its multiplicity. Now, knowing the multiplicity will help you graph the function itself. So the 0, if it's real, gives us an x-intercept. Then the question is, does the graph pass through the x-axis at this x-intercept, or does it merely come up and touch it and then retreat back to where it came from? That is determined by the multiplicity. So let's rewrite this. Further, if the multiplicity of c is odd, then the graph will cross the x-axis at c comma 0. So here's an example of what that looks like. Here's c. with an odd multiplicity, that means the graph is going to cross through the x-axis if it has odd multiplicity. And then if the multiplicity of C is even, then the graph will touch the x-axis at x equals C. So here's C with even multiplicity. So it comes in and it touches, and it does not cross. It simply touches the axis and then goes back to where it came from. It could have started on top, just like I have drawn here, or it could have started on the bottom, come up and touched it, and then retreated back down below the x-axis. So odd is cross, even is touch. Example 6. Find the zeros with multiplicities of the function f of x is equal to x minus 2 times x plus 3 squared times x minus 4. Then sketch the graph. So first we need to find the zeros and their multiplicities. So I'm going to write it out here. It's already factored. It's x minus 2, x plus 3 squared, and x minus 4. Set this equal to 0 to find the zeros, and then split it up and solve. So we would get x minus 2 is equal to 0, and that gives me x equals 2. When you have a factor that's raised to a power, you only need to take one version of it and solve when that one is equal to 0. So x plus 3 equals 0 gives me x equals negative 3. And finally, x minus 4 equals 0 gives me x equals 4. Now what are the multiplicities for each of these? Well, we go back and we look at the powers. The first one was x minus 2 to the first power. So this root, x equals 2, with multiplicity equal to 1. And we'll usually use this shorthand notation where m is representing the multiplicity. So m equals 1 for that one means that the multiplicity of the root x equals 2 is 1. The power on x plus 3 was 2, so that means negative 3 is a root with multiplicity equal to 2. And finally, the exponent on x minus 4 was a 1, so that means the multiplicity of the root 4 is 1. Finally, let's interpret what this means as far as crossing and touching. If the multiplicity is odd, then it crosses. So the multiplicity of the root x equals 2 is 1. That's odd, so it's going to cross at x equals 2. And it's going to cross at x equals 4. When the multiplicity is even, that means the graph just comes up and touches. And so when x is equal to negative 3, we have a multiplicity that's equal to 2, that's even. So the graph is just going to touch at the root x equals negative 3. Now let's sketch the graph. I'm going to start with the x-intercepts. I have an x-intercept at negative 3, so I'll put a circle there, dot. We have an x-intercept at x equals 2, and we have an x-intercept at x equals 4. One other thing that will help me with the sketch is the end behavior. Recall that the end behavior is based only on the lead coefficient. Since the f was given to me in factored form, I need to multiply a little bit of it out, but not too much. F of x is equal to, And I'm just going to use the x's. There's x, and then x squared, and then x. Now, of course, if these x's have coefficients, we would use those as well. All of the coefficients here are 1s, so there's nothing to see there. But what is x times x squared times x? That's 1x to the 4th. So we have an even degree polynomial with a positive lead coefficient. That tells me that on the left side it's going to go up. Right, so up left and up right. Now remember, this is just a sketch. It's just going to have the end behavior and the roots, and then that's pretty much it. We'll also get the crossing and touching of the x-axis as accurate as possible. We know that at x equals -3, the graph is just going to touch and stay on the same side. Based on the end behavior, we know that it starts above the axis, comes in and touches, and then stays on the same side because it just touches the x-axis at x equals -3. Then it's going to have a little maximum here somewhere. We don't know yet. Then it's going to cross when x is equal to 2. And then it's going to cross when x is equal to 4. And then meet up with the end behavior that goes up to infinity on the right side. So the graph looks something like this. We've captured the essence of this graph with its end behavior and its roots, but that's about it. Let's look at example 7. Find the zeros with multiplicities of f of x is equal to x to the 5th minus 4x to the 4th plus 4x cubed. Then sketch the graph. So the key to finding the zeros is to factor the polynomial first. So we're going to write this out. F of x is equal to x to the 5th minus 4x to the 4th plus 4x cubed. And the question is, what can I factor from all three terms? And that would be x cubed. When I factor out x cubed, that leaves me with x squared minus 4x plus 4. This leftover part is a quadratic, and we know how to factor that as well. And maybe you even recognize this one. X squared minus 4x plus 4 factors as x minus 2 squared. It's x minus 2 times x minus 2. From here, we can set this equal to 0 and solve for the roots. So here, the first one is x cubed. The cubed is the multiplicity. But what is the root? Well, the root comes from the inside, x equal to 0. And that one's already solved. So if you have x to a power with no plus or minus part, then that root is going to be 0. And so this is x equals 0 with multiplicity 3. The second part is x minus 2 equals 0. That gives me x equals 2 with multiplicity 2. If we talk about the behavior at the x-intercepts, we would say that at x equals 0 it crosses, and at x equals 2 it touches. The end behavior is based on the degree and the lead coefficient. So this is 1x to the 5th. So that means it's going to be down left and up right, based on the chart on the other page. Let's make a sketch. we have two distinct x-intercepts. We have one at 0, and we have one at 2. We have an in behavior on the left that is down. We know that the graph is going to cross through x equals 0 because of the multiplicity being odd. It's going to turn around, and it's going to touch the x-intercept at 2, and then it doesn't have any more x-intercepts, and it just keeps going, and it's up on the right side. So that's how you graph a little sketch of x to the 5th minus 4x to the 4th plus 4x cubed.